Good afternoon, everyone. Happy Monday. Hope you guys are glad to be back. We actually only, believe it or not, have about 2 weeks until the end of the third quarter. And because it's the end of the third quarter, we're going to, we'll have an exam right before that as well. So I know it feels like we just had an exam. That was last week on Monday. And those exams have been graded, and Miss Barbo is going to give those back to you guys. But this week is a kind of a normal week. We've got lecture Monday, Wednesday, and Thursday, and a quiz on Thursday. The quiz, I'll talk about this on Wednesday, but the quiz will cover basically the stuff we've gone over in Chapter 5 so far. So logarithms, exponentials, and then the stuff we're going to talk about today with inverse trig functions. That's the stuff that's going to be covered on Thursday's quiz. None of it is really new. A lot of it is review. Again, the book decides to take exponentials, logs, and inverse trig functions and separate those from the rest of the functions. I'm not exactly sure why, but that's the book's decision. So we're going to use this time just to review and solidify some stuff. So today we'll be over inverse trig functions, and I'll get to that in a little bit. Wednesday we'll start into a new topic in the middle of Chapter 5 on something called differential equations. We haven't talked about that before. It's a little bit new. We'll only be going through that for about 2 sections, but we'll get the very beginning of that prior to getting to that exam next week. So before we start in on inverse trig functions in section 5.8 and 5.9, I did want to go over 2 homework problems from the series that I gave you due today. And particularly they are section 5.2, numbers 13 and 23 are the 2 that I just want to briefly go over here. Okay, so let's do number 13. So we've got the integral of x squared minus 3x plus 2 over x plus 1 dx. And when you have a polynomial over a polynomial, so this is just a reminder, when you're faced with an integral of a polynomial over a polynomial, you're looking at the degree of each. In other words, the highest power of x. If the highest power of x on the top is bigger than or equal to the bottom, then you need to do long division. That's the first step you have to do with some of these problems. And we'll see this a little more today too. I'll go over another 1 or 2 that involve that. But what we need to do, we need to take x squared minus 3x plus 2 and actually divide x plus 1 into that. So if it's been a little while since you've done something like this, that's okay. What I need to do is look at x, and what do I need to multiply x by to get x squared? That's going to be x. I line that up with the x here. So x times x is x squared, plus x times 1 is x, and then I subtract. Okay, and x squared minus x squared, that goes away, and negative 3x minus x is going to give me negative 4x. So now I look at x, what times x is going to give me negative 4x, and that's going to be negative 4. So negative 4 times x is negative 4x, negative 4 times positive 1 is going to be negative 4. Then I subtract again, and what I get here is the 4x's go away, and then I've got positive 2 plus 4 is 6. So what that means is that this integral here ends up being the integral of x minus 4 plus the remainder over what I'm dividing by. This is my remainder. Okay. And now it's in a form that's much, much easier for us to anti-differentiate. So we've got x becomes 1/2 x squared, 4 becomes 4x. The 6 just comes along for the ride, and just like if we had 1 over x, this is going to be natural log of x plus 1. Please, please, please don't forget that plus c. That's killing some people here. If you don't have limits of integration, you have to get that plus c on there. Go through your homework and make sure that on any of those indefinite integrals, you left that plus c on there. Okay. All right, let's go over number 23 as well. Okay, 23. So I have the integral of 2x over x minus 1 quantity squared. Okay. The only reason I'm going over this one is that it should be pretty clear that I want to use u substitution. U equals x minus 1, du is dx. The issue, though, is I want to make sure you catch that you have to substitute for this x up here, too. And so you have to solve x is u plus 1. And so when you do this integral, the x becomes u plus 1, and then the bottom is u squared, and dx becomes du. So now we're at a place where we can actually divide things. So I've got 2u over u squared plus 2 over u squared. Okay. And the u over u squared gives me 1 over u with the 2 along there too. So 2 over u and 2 over u squared. So from there you should feel pretty comfortable that 2 over u is going to be 2 natural log of absolute value u minus 2 u to the minus 1. Again, plus c, do not forget that. And then we substitute back in. U is x minus 1. Okay? So that is our answer there. So hopefully that, you may have some other questions. Hopefully that clears up some questions you may have from those problems. So your homework for due today is the 4.6 problems, and then 5.2, 5.4, and 5.5. The 5.4, I think, a few of those problems were on differentiation, and those were just there to remind you about derivatives, so you can kind of get back in the swing of things. All right. So let's talk a little bit about inverse trig function integrals. This is a topic that we're only briefly covering here, and we're actually going to get into much more depth in Chapter 7 when we get into other integration techniques. So we're in section 5.8 and 5.9, inverse trig functions. Now 5.8 is just derivatives of inverse trig functions, which we've already gone over, but I wanted to just review those so that we're all comfortable with those derivatives. Now, I only asked you to memorize 2 of them, and I'm still going to stick with my word there. The derivative of arcsine and the derivative of arctangent. Okay, take a second and see if you can remember what those derivatives are. Talk to the person next to you. See if you can remember which one is which. One, I'll give you a hint, one involves a square root. Okay, do you remember these? Okay, the arcsine is the one that involves the square root, and it's 1 minus x squared. The arctangent one is 1 over 1 plus x squared. One way to remember which one goes with which, I don't know if you recall these trig identities 1 minus sine squared equals cosine squared, and 1 plus tangent squared equals secant squared. It's not a coincidence that those, sorry, my computer went blank here. It's not a coincidence that 1 minus x squared seems to look like 1 minus sine squared, and we're going to get to that in chapter 7 when we get there. Same thing for 1 plus tangent squared and 1 plus x squared. We'll get to, we'll see those relationships later. But that may help you, if you remember these formulas, then you'll remember these, it'll help you line these up. Now, you still have to remember that arc sine is, has the square root in it. There is a third one that I'm just going to list here in case you ever end up facing it. Arc secant. Arc cosine, the derivative of arc cosine, I think I mentioned this when we went over these before, is just the negative of this. The derivative of arc cotangent is the negative of this. The derivative of arc secant, it actually depends on how you define it. It gets a little tricky. But it's a little bit like arc sine, but instead of 1 minus x squared, you have x squared minus 1 under the square root, and you have an additional x down there on the bottom. So I'm going to kind of put these in parentheses here. You do not have to have that memorized. We are going to tackle more derivatives and integrals like these when we get to sections about 7.3 and 7.4, I think. Okay, before we get into integrals, I do want to recall to your mind how we plug numbers in here, because if we have some definite integrals or some other things that involve inverse trig functions, you're going to need to remember how to plug stuff into inverse trig functions, okay? So let's take as an example, how do we get the arc sine of 0? Now, when we talked about, let me write that a little bit bigger. When we talked about plugging numbers into inverse functions, like plugging numbers into natural log, or plugging numbers into cube root of x, or something like that. When we went over that, you recall that this equation can be flipped around into an equation that involves the function that we feel much more comfortable with. Okay, so arc sine of 0 is, what that means is the sine of something equals 0. So then we have to ask ourselves, what angle has sine 0? Now, sine is the y part. Remember, cosine's the x part and sine is the y part on the unit circle. So the sine of the angle 0 is 0, so this answer right here is 0. Okay, let's do a couple of other ones. Arc sine of 1/2. Okay, what that means is the sine of what angle is 1/2. Now you'll recall that on the unit circle, you've got this, there's an angle where the sine is 1/2, an angle where the sine is root 3 over 2, and then here the sine is actually 1. So this first angle where the sine is 1/2, that angle right there is actually pi over 6. Remember, all of these are in radians. We're not writing anything in degrees. What about arc sine of square root of 2 over 2? That's actually this middle one right here. And that, so the sine of what angle is root 2 over 2, that turns out to be pi over 4. Okay, if you recall, let me maybe draw up this, table one more time. So we had angles, and then the sine and the cosine of those angles. Okay, we had 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And the trick that I showed you here was to write the square root over 2 in everything. So everything square root over 2. And then we just go through and write 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So for example, the sine of, and I should write these in radians too, pi over 6, pi over 4, pi over 3, pi over 2. The sine of pi over 4 is root 2 over 2. Okay, so arc sine of 1 is the angle whose sine is 1. And that is square root of 4 is 2. So sine of pi over 2 is 1. So this is pi over 2 there. Okay? So that's how to compute values for arc sine. Arc tangent, the only thing you need to remember is tangent is sine over cosine. So for instance, if I say what is the arc tangent of 0, what I mean is what angle has tangent 0, and that means that the sine over the cosine is 0. So the sine is 0, and that's just the angle 0. Okay, so arctangent of 0 is 0. Arctangent of 1 is the angle whose tangent is 1, and that means the sine is the same as the cosine, because sine over cosine is going to be 1. So the angle whose sine and cosine are the same is pi over 4. So the arctangent of 1 is pi over 4. Okay. So we've gone over that a few times. I just want to kind of throw those out to make sure that that you guys are remembering how to plug stuff in if you get an indefinite integral there. Okay. So now we've got the derivatives written down. Let's go ahead and write down the integrals. So the flip side of this would be if I ask you to integrate 1 over the square root of 1 minus x squared, I get arc sine. Okay. Again, don't forget your plus c if you're doing an indefinite integral. Same thing for 1 over 1 plus x squared. You get arc tangent. Okay. So now how can we make this a little trickier? Now again, we're not going to explore this too deeply now. There are lots of ways that this can get trickier. But one way is instead of seeing x squared, you may see something else in there. So let me give you an example. So what if I had 1 over the square root of 1 minus 4x squared dx? Okay, instead of 1 over the square root of 1 minus just x squared. So what this should remind you of, this should remind you of 1 minus x squared underneath that square root. But instead of x squared, I have 4x squared, and I don't want that. I want just x squared. So you have to think, I'm going to do a u substitution so that I can end up with 1 minus u squared. But in order for u squared to be 4x squared, u is going to have to be 2x. Okay? So I'm going to do a u substitution, u equals 2x, so that u squared is 4x squared, so that this thing right here is u squared. And if I check, my du is 2 dx, so in order to substitute for my dx, I'm going to use 1/2 du. So I'm going to come in here then, and I've got my square root is 1 minus u squared, and my dx is 1/2 du. So I pull out that 1/2, and then everything else is set up exactly to be an arcsine integral. Okay, so that's 1/2 arcsine of u. Again, don't forget your plus c. And then I just sub back in for u. So u is 2x. Okay. So the key here is recognizing that that integral is really close to an arcsine integral. I just need to get this thing under here so that it's 1 minus u squared. Okay. Let's do another one. Let's suppose I had the integral of 1 over 1 plus 9x squared dx. Okay, again, this looks a lot like my arctangent one, except this is a little messed up here. So what I'm going to do is I want this to be 1 plus u squared, but in order to substitute in, I have to think through what do I square to get 9x squared, and that's going to be 3x. So I'm going to let u equal 3x. du is going to be 3 dx. So dx is 1/3 du. So let's just pull that 1/3 out front. What I'm left with is 1 over 1 plus u squared. And my dx is that 1/3 du. So now it's set up exactly to be an arctangent. So let's do that. So this is arctangent of u, and then I just sub back in. Okay, u is 3x. Okay, so if you see things that are really close to your arcsine or arctangent, you can do a u substitution to get them exactly where you want them to be. All right. Let me go ahead and write these up here just so we have them as we're going through this. One thing to keep in mind, especially for this arctangent integral, is that the arctangent one has a polynomial on the bottom. So again, you may run into problems here where you have a polynomial on the top and a polynomial on the bottom, and you may need to do a u substitution. Okay, so let me give you an example. You may need to do long division before you do anything else. So let's do an example here. Let's do 1 minus x squared over 1 plus x squared dx. Okay, that's my integral there. 1 minus x squared over 1 plus x squared. Okay. So now the top and the bottom are both polynomials. And notice that the degree of the top is 2. The highest power of x is 2, and the highest power of x on the bottom is 2. If they're equal or this one is bigger, you need to start with long division. And as a reminder, the way long division works here is you write the polynomial that's on the top first, and you do it in order of highest power of x first. So I'm going to write negative x squared. Let me write that a little bit bigger. Negative x squared. There's no x's, and then I've got a 1 there. You should have a space for each term, even if it's not actually there. Then you put a 0x or a 0 whatever term that is there. Okay. Same thing for the thing that that's doing the dividing. I write x squared plus 0x plus 1 there. And then I think through, what do I multiply x squared by to get negative x squared? That's going to be negative 1 So negative 1 times x squared is going to be negative x squared, 0x, and a minus 1. And when I subtract these, the x squareds go away and I get 1 minus minus 1 is 2. So this overall integral ends up becoming negative 1 plus 2 of the remainder. And now each of these is in a format that I can actually easily anti-differentiate. So the negative 1 becomes negative x. The 2 is just left alone, and this is 1 over 1 plus x squared. So that's just arctangent. Okay, and then again, don't forget your plus c there. Okay. Any questions? That makes sense. Okay, now one caution that I have is that you need to be careful that just because you see like 1 plus x squared or the square root of 1 minus x squared, that doesn't necessarily mean that it is an arctangent. So let me give you an example. So something like this. That square root of 1 minus x squared on the bottom tempts me to try to do something with arctangent. However, that's not actually how you should approach this problem. So the first technique that we ever learned was substitution. And one of the reasons that we learned substitution as our first technique, and as we do more techniques later in chapter 7, we're going to do them in a particular order. Typically you always look for substitution first. Well, you try to do the integral if you know how to do it. But this one I don't immediately know how to do. It's not 1 over square root of 1 minus x squared. So the first thing that I try is u substitution. And in this case, u substitution is actually what I need to do. I need to say u equals the inside of that square root. And so then du is negative 2x dx. And that x here is the derivative, is part of the derivative of that inner thing. So that x dx is negative 1/2 du. So what I'm going to do here is I've got 1 over the square root of u, and the x dx becomes negative 1/2. I'm just going to stick that out front. Du. And now we're in a place that's much, much easier. This is u to the minus 1/2. So when I anti-differentiate that, I get u to the 1/2 divided by 1/2 or multiplied by 2. Okay, so that's a nice cancellation that happens there. So I've got negative u is 1 minus x squared, so I've got the square root of that. Okay, so this integral is just there to remind you that not always when you see that square root of 1 minus x squared are you going to try to jump into an arc sign. Okay. All right. I've got one more that I want to show you. One last example that I want to do here. Okay, let's do the integral of x plus 3 over the square root of 1 minus x squared. All right. Now here, this might not be entirely obvious, but if one way to think about this is if we didn't have the plus 3, you'd do the integral that way. That was one of our examples that we just did. Okay, if we didn't have the x, how would we do that integral? If it was just 3 over square root of 1 minus x squared, that's just arctangent, right? I mean, sorry, arcsine. So what I'm going to do is actually just split this. If I've got a plus b over c, I'm just going to write it as a over c plus b over c. I'm just going to write it as the first thing divided by the square root plus the second thing divided by the square root. Okay. Remember that with fractions you can do that if you're doing addition on the top and there's only one thing on the bottom. So what that allows me to do is split these two integrals and use two different techniques on them. The first technique I would use u substitution. We just did that over there. I'm not going to do it again. But this second one is just a straight up arc sign. So we did the first one. I'm just going to copy that over here. Right. And then the second one, that 3 just comes out, and we just have a straight up arc sign plus c. Okay, so you may need to split the integral into two different integrals. It's a little bit kind of like, if you remember when we had a problem like x plus 3 over x squared, we would actually split that into x over x squared plus 3 over x squared, and those are each separate things that I can actually do. Okay, so this is kind of overall, this can get much more complicated, and we're not going to dive into a lot of that right now. We are going to dive into some of that in chapter 7, but for now this is about as far as we'll go with inverse trig function integrals. So you should have some time today to work on. If you have any additional homework questions, you can ask those. Otherwise, you can go ahead and work on the homework due on Wednesday, which involves these integrals, and ask questions on those if you have them. So have a great rest of your day, and I'll see you on Wednesday.